Okay, this is March 17, 2022. So what we're going to do today, we're going to continue the chapter on capacitors, and we're going to calculate the energy inside a capacitor. Okay, so here you go. If you want to calculate the gravitational potential energy, okay, if you want to pump, let's say, if you want to pump gravitational potential energy to this bottle, what do? We separate this bottle from the earth. We raise it. Make sense? Okay? If we want to create electric potential energy in a capacitor, we do something similar. Okay? But one way to create potential energy in a capacitor would be to have a positively charged capacitor here and another negatively charged capacitor here. That's one way. Okay, if you keep the charges to increase the potential energy of the system, what you have to do? You have to separate them. Okay, so let's say to pump potential energy in this bottle, we raise it against the Earth's gravitational force, right? If I have a positively charged plate here, a negatively charged plate here, if I want to increase the potential energy of this system, the positively and the negatively charged plates, I separate the two charges from each other. Make sense? It's like raising it, raise one of the charges against the electric field of the other charge. Make sense? So, there is another way to do the same thing. There is another way to increase the potential energy of a capacitor. Remember, that's the definition of a capacitor, right? Two pieces of metal. Two pieces of metal. They are initially discharged. This is exactly what happens during a real life, okay? And they are also fixed in place. It's very important that they're fixed in place. What do? Suppose that I can go ahead, get my hand here, and shove it in one of the capacitors. Here you go, would be the get some negative charge and move towards the other. Can you picture that? As we do that, what's going to happen? I leave a positive, a net positive charge behind that's going to prevent the negative charges from moving, unless I force the negative charges to go towards the other metal. Make sense? That's exactly the case of raising the bottle against the gravitational energy. This is exactly the case as raising one positive charge and a negative charge against, from each other, separating them from each other. Okay? So here you go. That's a kind of thought experiment. We do that all the time. Einstein used to do that. I believe it was Einstein who invented the word thought experiment. So here you go. You get some negative charges, take it out from the first metal. It's gonna be difficult to move it because there is some positive charges attracting those negative charges. And then what you're gonna do? You're gonna, oh, here you go. Here's the force, right? Here's the force. Here's the force of my hand. Here's the electrical force. And then what you're going to do? You're going to have to shove in the other metal. Make sense? And because those two capacitors are fixed, they are not going to attract each other. Because they don't attract each other, but they are fixed now, we can say that there is some potential energy in the system. Okay? Here you go. Keeping those two plates, those two metals, at rest is like keeping this bottle here at this height. Okay, it has potential energy, which, if I am smart enough, I can use it to do some sort of useful work. Make sense? Okay, and then if you want to increase the charge, you keep on. Oh, here you go. Now we have the two metals attracting each other, but they are not moving because they are fixed. Because they are attracting each other, it means, because they are attracting each other and they are not moving towards each other, it means that they have some potential energy. This potential energy is electric potential energy. Okay? So here you go. We start with a small amount of charge on the left metal, on the left piece of metal, and a small, amount of negative charge on the other side. Okay, because we have this difference in charge between one another, we create a difference of potential. Okay, every time that we have a charge distribution, we have a difference of a potential. If we have a difference of a potential, we have potential energy. Okay, there is a relationship. Remember that there is a relationship between electric potential and potential energy. Okay, so here you go. So that's the idea. How do we take advantage of this simple illustration and calculate the amount of electric potential in these two capacitors, in these two metals that became a single capacitor, charged capacitor, and now has some electric potential energy, right? There's a smart way to calculate that, okay? So let's go here to the, okay, so here you go. Remember, the work done by the hand, right, is the force that the hand exerts on the electric charge dot ds. And the electric potential energy is going to be minus this work done by the hand. Okay, so here you go, and here you go. So what we end up getting, remember that the electric force is going to be the amount of charge times the electric field. Okay, and you already know that the electric potential energy is equal to the charge times the electric potential, right? You already know that. Okay, so when I'm doing my experiment, I am initially transferring a very small amount of electric charge. Okay, exactly what we saw in that illustration. Here you go, right in here, right? So the potential energy created by that is going to be the electric potential times the Q, the infinitesimal electric potential energy. The infinitesimal electric potential energy, okay? Let's do that. Here you go. I'm gonna go on the other. I'm gonna write down here. Today is insert page break 317. Oops, 317. Oh gosh, 317 2022. Okay, so we are going to calculate the electric, the amount of potential energy in a capacitor. In a capacitor. Okay. Why do we need that? Well, we need that to find out how much energy we have to do some useful work. Okay, that's why. It has some practical applications. Okay, let's say a battery maybe has some energy in there. The energy can be measured either in joules, or there's another way to measure energy. It's kilowatt hour. Have you heard of kilowatt hour? Huh? In your electrical bill, if you look at your electrical bill, how much energy you used, they put kilowatt hour there. Kilowatt hour is a unit of energy. There is a there's a relation between kilowatt hour and joules. Okay? So that's why we want to know what's the potential energy, for instance, in a capacitor, or potential energy in a battery. Okay? So we're going to calculate the amount, not the amount of potential energy in a capacitor. Okay. We do that by imagining that we are removing, that we are starting with a uncharged capacitor, and little by little we extract electric charges. Let's say negative electric charges, right? That's easier to do that. Negative electric charges from one conductor. We can do that by hand, right? Here you go. We can do that. Here you go. Can do that by imagining the following. Imagine the following. Here you go. The following. One. Starting with an uncharged capacitor. Start with an uncharged capacitor. Here you go. Capacitor. Little by little. Little by little. No, not little by little, right? First, we shove, shove. Suppose it's possible to do that, okay? Shove our hand in one of the conductors and extract negative electric charges. Then we move those negative electric charges from one conductor to the other. Okay? I'm just spelling out the step-by-step that is illustrated in that drawing. One conductor to another. Remember, what is a capacitor? A capacitor is two conductors, right? So I have to refer, when I say capacitor, I'm referring to two conductors simultaneously. When I refer to a conductor, it's going to be one of them. A single conductor is not a capacitor. Okay? A single conductor is not a capacitor. A capacitor is a device that has two conductors or more. Okay? It's possible to have more too. Okay, then we move those negative electric charge from one conductor to the other. 4. And shove the negative charge in the second conductor. Okay, here you go. The action of moving negative charges from one conductor to the other means that these negative charges are being prevented, are being attracted, not prevented, but are being attracted by the positive charges that were left behind in the first conductor. Okay? Every time that you must make an effort with your hand to move an object that is being attracted by another object. It doesn't have to be attracted, it can be repelled too, okay? Every time, so we can be even more generic. Every time you must make an effort with your hand to move an object that's being attracted or repelled by another object, you pump potential energy into the system composed of these two objects. Okay? It's a very important idea to keep in mind. There is a very close relation between energy and force. Okay, so much that the definition of potential energy is the force dot ds, right? Force, of course, I'm referring to force, to a conservative force. Okay, so how do we do that mathematically? That's the, okay, how do we do that mathematically? Oh, we can state, remember that there is, remember, to calculate the potential energy. Now we're going to get into the actual calculation. To calculate the potential energy in a system, remember that the following relation. Okay, insert. Let's see. I use potential energy as W. Why doesn't go there? Ah, gosh. Sometimes the thing doesn't work the way it's supposed. Okay, here you go. In there, in my notes, in my published notes, I use the potential energy as being W sub E. Okay? That, remember that another way to write it down, right? Should be delta U. Remember? Another way that to write it down. But there in that specific chapter of my notes, I wrote as being W sub E, but I actually meant delta U, difference in potential energy. Remember that difference of potential energy is, Q times difference in electrical potential. Okay? We're going to simplify this notation by rewriting it as U equal to QV. Simplifying the notation. Okay, we have, okay, if we move an infinitesimal amount of charge dq, we have the infinitesimal amount of potential energy du. Okay, if we move an infinitesimal amount of charge dq against an electric potential, against an established electric potential V, we have infinitesimal amount of potential energy. Make sense? And we have an infinitesimal amount of change of potential energy. That would be better. Here you go. Ooh, which one that I want? du, we can here write down as being that du V times dq. Okay? How do we go further than that? I didn't found a relation yet. How can we get out from this spot and calculate the total energy, right? Oh, well, you have to integrate both sides, right? Right? But then after integrating both sides, what else do you do? Well, there's a little trick. There's a little trick, mathematical trick that we usually discover. Let me show you one. Okay, we're going to start with a sample case of a two parallel plate capacitors. Okay, two parallel plate capacitors. We know, separated by a distance L, we know that electric potential is going to be the electric field times L. Let's start with this one as an example that that we know, that we already know what's the relation. Okay, and then okay, let's so the idea here, the proposition here is the following. The proposition here is the following. Is the following, you know. Calculate the amount of potential energy stored in a parallel plate capacitor with plates separated by a distance L. Okay? When you are exploring a new problem, you never try to derive the most generic equation. You never do that. Deriving the most generic equation through the most generic situation is very difficult. Okay? And most likely you're not going to succeed in deriving the equation. So what do we do? Okay, we start with something simple, something simpler that we know we are going to succeed, and it's going to give us a good motivation to continue our study. Okay, so what do? We start with this simpler problem of the parallel plate capacitor, which, by the way, has a uniform electric field, right? Okay, this is the most simple. This is the simplest type of capacitor you have out there, because you know the simplest type of capacitor you have out there, and easiest to treat, because it has a uniform electric field. Okay, so V, here you go. Treat that as though as it's a problem. Okay, so treat like that as an example. Calculate the amount of potential energy in a parallel plate capacitor with plates separated by a distance L. With a non-charge density, with a non-surface charge, with a non-uniform, here you go, I gotta put that too, uniform surface charge density, sigma. Okay, I'm not gonna write sigma there. This is the simplest type of capacitor you have out there, the easiest one to treat mathematically, and the easiest one to treat mathematically, because it has a uniform field. Okay, so here you go. For the parallel plate capacitor, remember? For the parallel plate, so for the parallel plate capacitor, the above equation becomes, you know, we go E times L, right? And E is what? E is sigma over epsilon naught, right? Remember that? You know, it comes to a point that is very useful for you to memorize certain relations. That of the parallel plate capacitor, epsilon. Okay, and let's not forget that sigma is what? Sigma is Q over A, right? The charge in the capacitor. Well, the charge in the capacitor means the magnitude of the charge in one of the plates, in one of the conductors, right? That's what it means. Because the charge of capacitor, the net charge in the capacitor is 0. the net charge. But I'm talking about when we say the charge in the capacitor, we mean the amount of the magnitude of the charges in one of the plates. Okay, that's what we mean. Here you go. Q divided by A. Here you go. So look what's happening here. Did you see something here that becomes very useful? You know, when we had this equation, we didn't have a clue how to solve this integral. We didn't have a clue how to solve this integral. The integrating variable is the Q. But after playing a little bit with that, what did we find? I'm going to make it even easier for you to understand what's happening here. I'm going to put this Q here, right in here, and this L right in here. Okay? If if I integrate this equation, will I be able to solve it easily? What we have here, we have L, that's a fixed value, right? A capacitor will have a distance between the plates, between the conductors, that's fixed. We have an area, that's also going to be a fixed value. We have epsilon naught, that's a fixed value. And what we have, what else we have? We have QDQ. Make sense? Easy to calculate that, right? Now we are going, if we are going to integrate, here you go. If we are going to integrate, I'm going to, here you go. I can put the integral right in here. Okay. And remember, we are charging the capacitor from no charge. We start with no charge whatsoever, right? So the initial charge here, we're integrating over the charge, so the initial charge here, Q, has to be 0. Until, a given charge amount that we put in there. The energy of the capacitor is going to be dependent on this final charge that the capacitor reaches. Okay? So here you go. Do you see what happened? We start with something like that we didn't had a clue how to calculate. But just looking at one specific special case, we figure out that we can calculate the integral. Okay? Which, by the way, is a very simple integral. Let's continue that. Here you go. We're going to have Q squared over 2. Here you go. And then I have to apply the limits. Some time ago I found this PDF document that has all the keystrokes for this thing here. It's somewhere here in this computer. I cannot remember. I memorized some of the keystrokes, but I don't memorize all of them. The keystrokes are much quicker than go after those things here. Yeah, and I still didn't get the right one anyway, but that's okay. Right, now I don't need that. From Q equals from 0 to dq. Okay, and look what we get. We get an electric potential energy that's going to be a function of the charge, the final charge distribution in the capacitor. Let's see if we can do better than that. Let's see if we can do better than that. Do you remember? What is the capacitance of a parallel plate capacitor? Do you remember? Let's go. We derived that in class. Let's go back here. Capacitance of a parallel plate capacitor, we derive it. What is it? What is it? Spherical. We did a spherical. We did. What else did we do? Capacitors and dielectrics. Let's see. Simple numerical example. Fine. Okay. Metallic this same size. Okay, that's the one, right? Did I calculate that? Yeah, right in here. Parallel plate. Remember that? The capacitance of a parallel plate capacitor. It's very difficult to memorize all of that, right? That's why you have to build up a little table. Okay. It's something like that. I'm not gonna put D here, I'm gonna put L because I'm not using D is the separation of the plates. For this problem, I'm using L as the separation of the plate. Note, see that we have, epsilon L, epsilon naught A is this term here, right? And the L is this one here, right? So what we are going to have? We are going to have for the parallel plate capacitor that U is going to be the inverse of the capacitance times Q squared divided by 2. Okay? So let's take a look at our notes here. You go. If we did everything right, you go. Yeah. We can do something else. We can do something else. Okay? We can here write this relation in a different way. We can here write this relation. Just remember, be reminded that okay is Q. Yeah, capacitance is Q over V, right? We can have another relation for this potential energy. Okay, we have actually 3 equations that means exactly the same thing. And then we pick up the one that's easiest to memorize. Okay, we can here write my Q as being CV. Q equal to CV. Okay, and when we do that, let's see what we get. It's always good to keep on exploring different relations so we can find out whether we can get a relation that's easier to memorize. Do you think it's easy to memorize something like that? 1 divided by Q squared divided by 2C. Gotta think about yourself. Think about yourself whether it's easy or not. But let's take a look at this one. We're gonna get C squared here and V squared, right? Here we go. Oh, not what I want. Yeah, that's what I want. Nope. Let's do it again. Here you go. Okay, so here you go. And look what we get. We get an interesting relation here that's rather easy to memorize, right? It is as though this thing is like a kinetic energy equation. Does it remind you of the kinetic? It's not kinetic energy, of course, but half of CV square. Kinetic energy is half of mv square, right? So if you have to memorize something, I would I would prefer to memorize this one than to memorize this one. Can you get another relation? Let's see. I wrote that down in terms of Q. Let's let me see. Let's substitute the C now. C is Q over V. Yeah, let's put the C right in now. Let's see if we can get something. Yeah, C now using the relation for C, right? The very definition of capacitance. Here you go. The very definition of capacitance. Q over V. I don't want this half here. I want this half right in here. Three different equations for the same thing. Half QV. Which one do you think is easier to memorize? I still think is the CV square. Okay, three different relations for the energy in the parallel plate capacitor. I'm telling you, the parallel plate capacitor. Because I used the electric field for the parallel plate capacitor in my equations. Okay, here you go. Three different ones. Okay. I would rather write this equation. Let me see. How would I rather write in this equation? I would rather write this way. Here you go. Like that. Let's write this way. Or maybe, you know, put the half separately. Huh? Put the half separate. Here you go. Q square over C. Okay. Now there is a little secret that you have to believe in. I'm not going to prove that. I did this derivation for the potential energy of a parallel plate capacitor. And yet, when you do for every other capacitor, cylindrical, spherical, triangular, or, you know, odd shaped, what happens? We get exactly the same relation. CV square, QV half, Q squared to half of Q squared over C. It doesn't matter what the geometry of the capacitor is, okay? We're not going to do that here, but you have to, okay? Okay, so let's finish that. What else we need to do? You go V. Yeah. Okay, here you go. CV square, right? Half CV square. There is another way to write something else here. Going back to the equation of the electric potential energy. That we got for the electric field. Let's see here. This one right in here. Going back to the equation. Okay. The equation here. Um, yeah, okay. So no, we don't want to do that. What we want to do is to go back. Here we go. To this one right in here. Okay? Going back to this one right in here. For the parallel plate capacitor, what we have? For the parallel plate capacitor, we have uh, epsilon naught A over L. Okay? And what else? EL. EL, like that. So we go ahead. You know, there's one more thing that we can do here. That's very important. I calculate the potential energy. Now I'm going to calculate something else. Okay, I'm going to calculate it. Let's continue here. With this relation, L cancel out with L. This guy becomes L right in here. Okay, here we go. Electric field. I'm gonna put right in here, and now we have this term here that you may recognize. Okay. Remember, we have the plate, planar plate. This planar plate has an area, two plates at a distance L. So what we have? We have here a volume, okay? If we have two disks, the volume is going to be a cylinder, right? If we have two square plates, the volume is going to be a parallelepiped, and so on, right? So what you see right in here can be rewritten as a volume. And I'm going to write with lowercase v, so you don't get mixed up with the electric potential. And now we can write down something else. We can pass this lowercase v to the left side. Okay? And what we get? We get, let's see here in the left side, is the energy density per unit of volume. Okay? So you have energy, and then you start asking, how much energy do we have? What's the density of energy in a given volume? Okay? Okay, the higher the energy density, the more energy you can find in a given volume compared to others. Okay? And look at the relationship here. The relationship is half epsilon naught E squared. Very similar to the kinetic energy relation, right? It's a constant, right? And we have an electric field here. So what we have, what we can say is that from the above equation states that the electric field itself has some energy stored inside it. Okay? So now we have this, this thing that has that's an that's invisible, that has no mass whatsoever, and yet it has some energy. Okay, and you can take advantage of the energy of this something that's invisible and doesn't weigh anything. It doesn't have a mass, but it has energy. Okay, this bottle has a mass and it has energy. Okay, but the electric field, no. You go inside your parallel plate capacitor, look at the energy, the electric field here inside, and that small volume of here inside between the capacitors has some energy. And that small volume may not have any mass whatsoever. You can have two parallel plate capacitors there in the vacuum, okay, charged, and whatever is here in this volume, in this vacuum that has no mass whatsoever, no particles whatsoever, it has energy. And now, if you are smart enough, you can figure out how to use that energy here in between those plates. Okay? If you are smart enough, you can figure out how to tap into this energy that has no mass, doesn't weigh anything. What time is that? 5:41. We still have some time. And what I have to tell you is, okay, the above equation, okay, the energy density, the above equation states that the electric field has inspired energy. Let's see, the left side of the equation, is called the energy density, and it states that the electric field itself has some energy stored inside it. Although, here you go, Although the above equation was derived only for the parallel plate, okay, capacitor, it applies to any capacitor. Not just any capacitor, but any electric field too. But also any electric field in space. Okay, so that's the story that we have here, and remember this equation. Later on, we're going to see something like that too, not for the electric field, but for the magnetic field. Okay, let me give you, and we're going to derive, right in here. Okay, so what I'm doing here's the energy density of the electric field, right? And I'm here writing that with the subscript E. Why am I doing that? Because there is something else called the energy density of the magnetic field. And look at the relation. It mirrors the relation of the electric field. It's an electric constant. Here's a magnetic constant. Half, half. Here's the electric field. Here's the magnetic field. They're both squared. Okay? So they mirror each other. It's 5:45 now, and I'm gonna finish. Let me check our syllabus here, just to remind you, right, about the exam. The last one is the fifth, version 5. And by the way, did you see your? Let's see. Today is the 17th. Yep. Okay. So we are going to start current and resistance today. And now we are going to start understanding better those experiments that we did. We did the experiment on measuring the resistance, and then we did the other experiment of the current in a circuit, right? We're going to start understanding this experiment better because we're going to start talking about it. Don't forget, exam Tuesday, right? 7, it's going to open 7 to midnight. 7 p.m. to midnight, pick up 2 hours interval. If we start the exam at 11 o'clock, you're going to have only 1 hour. Don't do that. Don't start at 11 o'clock. You can start at 11 o'clock if you want, but you're not going to you're going to have only 1 hour to do the exam. Okay? Ideally, you should start the latest at 10 p.m. The latest at 10 p.m. Okay? Any questions? No? Yeah. Huh? No, no lab Monday. No lab on Tuesday, right? No lab on Tuesday. Every time that we have an exam, there is no lab. Okay? No, Thursday, no. Well, Thursday, let's see, it's Thursday. No, I have another lab. I have physics 37 on Thursday. So, no. The next lab is going to be when? It's going to be, we're going to have a holiday. Cesar Chavez, we're going to have a spring break. Wow. Yeah, after spring break. It's going to be how many weeks since the last lab? 1, 2, 3, 4 weeks. 1 whole month without a lab. Are you happy? Okay. Everything that we're doing in the lab has practical applications, okay? That is very nice that you can be exposed to multimeters, resistors. If you're gonna go into research, engineering, you have to know that stuff to understand your circuit, your electronic circuit. Just yesterday, I was talking to this guy in Brazil. He's very good at doing projects, electronic projects. And there's some people here has ever played with Arduino. Who has played with Arduino here? Yeah, here you go. Good. Let's get together. You gotta help me with my project. I got a project there in Brazil now. I got a $250,000 project there in Brazil, and I need to build some little toys. This guy there in Brazil was teaching me how to turn on my LED strip. You know? But it's not just turn on the LED strip. You also have to put it nicely, no wires sticking out, make everything very reliable and so on, right? Do you know how to do that, Faust? You know? Okay. So let's talk about that. And what I'm going to do here, I'm going to take attendance now. Excel. Today is, this is research. Mario Jimenez Acevedo? No, he used to come, right? No, he's stopping. No, he didn't used to come. Oh, he comes only for the lab. Toby, are you there? Okay. Harun? No. Musa? No. Jennifer? No, Jennifer, no. Genesis? No. Jennifer? No. Robert Faust is here. Pedro Flores? Good. Lawrence Flores? Good. Alexander Garcia? Song? There. Brian Inez? Atina not here. Dylan Martinez? Rafael Mercado? Okay. Alexis Nigret? Nope. Abraham Perez? Nope. Are you folks planning to take any course in the summer? Huh? Are you? Where? Here? Any physics? 39? Yeah? Where? Here? They're offering here in the summer? Oh, really? Okay. If they're not, okay. If they're not, I haven't heard from them yet. Okay, I haven't heard from them yet. So, but it looks like they're offering at least their LA Southwest. Oh yeah, yeah. At LA Southwest is gonna be online. If they offer here, I do not know if they're gonna do online. Okay, so they hired me to do the online physics 39 there. They hired. They told me that they're gonna hire them, right, for the LA Southwest. So far, they didn't tell me anything about teaching here in the summer. So Ramon Quintana, okay. Ali, there. Kenny Villa Gomez, good. Patrick Villavazov, and Nolan Williams. No. Let's see here how many we have. 13. 3. 13. Okay, 3, 6. No. Those are 3. Okay, good. Let's go for our break. And is what? 5:50. We're talking about 6:05 break. Break till 6:05 p.m. And okay, so now capacitors and dielectrics. Let's talk about capacitors and dielectrics. There's something I didn't tell you. What you see right in here? That equation for the parallel plate capacitor, the capacitance of the parallel plate capacitor. Okay. This equation here for the parallel plate capacitor didn't tell you something. The equation of the capacitance of the parallel plate capacitor, you know, it's for a special type of capacitor. I didn't tell you that. Just put it, I didn't tell you that. Right? But now I'm going to tell you. Is a capacitor that has vacuum between the plates. Okay? Nothing, right? Can be air, but if you want to be strict, just suck out all the air from between the plates, and that's what will be the capacitance of this capacitor. Clear? Okay? So if you put something else in between, if you put something else in between, this something else must be a dielectric. Dielectric, then the capacitance equation becomes slightly different. Okay, so let's take a look. So here the I don't need that anymore, right? So here you go. So vacuum between the plates of a capacitor, nothing in there, and that's the capacitance. Is that equation that you saw? Epsilon naught A over L. Okay. So here you go. Vacuum between the plates of a capacitor. We have this electric field. What if you put something else there in between? Can be a piece of cardboard, can be a piece of glass, can be a piece of plastic, can be air, okay? When you do something like that, something happens, something else happens. The electric field, we still have an electric field. It's not going to be necessarily the same, okay? But we're still going to have an electric field. We're still going to, and what's going to happen? Here you go. The electric field that we have is going to act in the molecules of this dielectric. Can you picture that? And we can represent that by those molecules here being stretched out. Okay? The negative charge of this dielectric are going to be attracted towards the positively charged plate, and the negative charges of the plate is going to attract the positive charge. Can you picture that? Okay? That's what this initial electric field is going to do. The electric field is going to polarize those molecules. It's going to polarize the dielectric. And when the dielectric is polarized, what's going to happen? We are going to have an electric field within the dielectric. Electric field goes from the positive charge to the negative charge. Can you picture that? And because the electric field of the plates is from the right to the left, and the electric field of the molecules that have been polarized from the left to the right, the net field is going to be weaker. Okay? The net field inside the plate will be smaller because of the field of the polarized molecules. So if I had 1, 2, 3, 4, 5, 6 electric field lines here, because of the polarization of those molecules, I'm going to have less. I'm going to have maybe 3, okay? And I'm going to even change the color so it's clear this is a different field. So that's the qualitative idea of what happened inside a capacitor that has a dielectric. We get a weaker field. Okay? So here you go. Vacuum, put the field there, put the dielectric there, the field becomes weaker because of the polarization of the molecules. Okay? Dielectric in vacuum, the dielectric is vacuum, dielectric is another other than vacuum. The intensity of this electric field is going to depend on the dielectric. air, glass, water, cardboard, plastic. Okay, the field that you end up having here is going to depend on the okay, on the dielectric that you put in there. Here you go. Let's see. I'm gonna copy that and I'm gonna put it here. And that's the qualitative idea that you have to have. You know, it's very important to have those qualitative ideas because it gives you a more solid ground to solve your mathematical problems. Let's see what you have here. Okay. Okay, so that's what the idea to have, and let's go the next step here. That's the qualitative idea. Now let's go to the quantitative treatment. Okay, so here we go. Start with the dielectric plate. Here's my notes. Put a piece of dielectric between, right? The molecules are going to be stretched. The molecules of the dielectric are going to be stretched. They're going to be polarized. Because the molecules are polarized, they generate a field, a polarizing field that cancels out the outside field of the capacitor, resulting in a weaker electric field. Okay, so instead of having a dielectric field given by, sigma over epsilon naught, you're going to have something else that's going to be given by epsilon naught divided by kappa, where kappa is going to be greater than 1. Okay, E naught greater than, okay, and again, kappa is a characteristic of the dielectric material. That's what you have to know. Okay, and if you're going to solve any problems, you have to know what the value of kappa is. So what are the consequences? There are some consequences here. Electric field weaker. Okay, so here you go. Let's write it down, the notes. Then not only the capacitance equation becomes slightly different, initially, so the very core here is that the electric field becomes different, okay? So let's go step by step, step by step. I'm just gonna repeating, writing what you saw in the drawing, okay? If you insert a dielectric between the plates of the capacitor, the following will happen. 1. The external electric field of the capacitor will stretch or polarize the molecules of the dielectric. 2. These polarized molecules generates an electric field that is contrary to the external field. As a result, the net field inside the dielectric will be weaker than the field if we had vacuum between the plates. Okay, so here we go. So the final electric field, is going to be just like you saw before. For a parallel plate capacitor, let's say, field magnitude is going to be sigma divided by epsilon naught. Okay, I will call this field now the E0 field. E0 is the field of the vacuum. Okay, E0 is the field with vacuum, which is a dielectric, by the way. Vacuum is a dielectric between the plates. If we insert a different dielectric, we get another field E. That's gonna be less than E0. Or the way we write is going to be, don't forget, E0 is the field when the dielectric is vacuum. Kappa K greater than 1. K is the dielectric constant. That's what happens to the electric field. Okay. What happens to the other parameters? The other parameters, okay? Let's see what happens to the other parameters. We're still talking about the parallel plate capacitor. That's the easiest one to study. Okay. So here you go. What happens to the electric potential? Right? Let's see what happens to the electric potential. Because it's a uniform electric field, what happens here? Okay, what happens to the other parameters? What happens to instead of the other parameters, what happens to the electric potential? Electric potential. Okay. Because the field will still be uniform, okay? The electric potential can be written as the new electric potential can be written as, here you go, V E L. Okay? And let's take a look here. Here you go. We start with the electric field and you derive everything else. Here you go. It's going to be something like that, right? And then E naught L is what? Is going to be the electric potential with vacuum between the plates. Okay? Just like the field, the electric potential also decreases. The electric potential also decreases. So the system loses energy. Okay? In other words, the system loses energy when we insert a dielectric in between the plates. So let me give you another example of a system losing energy. Okay, so where's my bottle? Here you go. Here's my bottle. My bottle has some potential energy here, right? I'm gonna make this guy lose energy, potential energy. What's gonna happen? He's gonna fall. He's gonna seek a place with smaller energy. Okay, and so something interesting happens when you insert a dielectric between the plates of the capacitor. Okay, all the system out there, they all try to reach a state of smaller energy. This piece of plastic try to reach a state of smaller energy, which is smaller potential energy, which is at the top of this table here. It's the same thing with capacitor. If you have vacuum here between the capacitor and you approach little by little a dielectric, what's going to happen? The dielectric is going to be sucked by the capacitor, naturally sucked by the capacitor. Okay, so that's exactly what happened in real life. Okay, and because of that, it loses energy. Okay, so that's one. Two. What about the capacitance? What about the capacitance? Okay, 624. Here we go. Let's not forget capacitance by definition, right? Let's start with the capacitance, capacitor in the vacuum. It's going to be what? Q, right? Divided by V naught. That's the capacitor. Okay, here we go. Capacitance, vacuum between the plates. Vacuum between the plates. Any dielectric between the plates. Any dielectric between the plates. Any dielectric between the plates. I'm going to write that as being C Q over V, right? Okay, so when we put a dielectric here, the amount of charge doesn't change. Okay, so why is that doesn't change? There's a reason why it doesn't change. Why that it doesn't change? If I have Q here, the capacitor is charged Q in the dielectric is vacuum, and then I put another dielectric different of vacuum. Does the charge change or not? And if it does or does not change, why is that? There's a reason for that. Think about that. Think about that. You know, the dielectric, what you have here is a dielectric material. Okay? Dielectric material do not conduct charges. Okay? So the charges that are in this capacitor, we will not be able to migrate towards the dielectric. Make sense? It doesn't migrate to the dielectric. We won't be able because we have a dielectric here that doesn't conduct charges. If you put a metal here, that's a different story. If you put a metallic wire between those two plates, then you're going to discharge the capacitor, okay? So I can tell you with conviction that the charge here for the capacitor with the dielectric is going to be the same as the charge with the capacitor without the dielectric. Now, you also know that the electric potential changes, right? So we already calculated the electric potential. Here you go. Let's see what happens to the capacitance when we put a dielectric there. Here you go. Kappa. Kappa. Here you go. What happens to the capacitance? The electric field decrease. The electric potential decrease. What happened to the capacitance? When we put a dielectric there other than vacuum, it increases, right? Because kappa is greater than 1. You know, in conclusion, when we insert a dielectric between the plates of a capacitor, comma, the electric field decreases, the electric field decreases, the electric field and electric potential, and the electric field and potential decrease, but the capacitance increases. Can you remember that? Possible to prove that, right? Mathematically. And that's exactly what I did. Okay, so here we go. And what about the energy? Let's see what happens to the stored energy. Let's see what happens to the stored energy. Here we go. Again. What about the stored energy? What about the stored energy? Okay, so if you remember that equation, right? Half CV squared, U is half, U is half CV squared. Okay, here we go. We get kappa C naught V squared okay, V squared becomes, we go, oh wait a minute, let me write down the other one first. I didn't write down the other one first. What about stored energy? Vacuum as a dielectric, right? I'll write that down first. So I'm putting that naught just to remind you that we are talking about vacuum. Okay, here you go. Here you go. Dielectric other than vacuum. Vacuum. Half C squared, right? So let's see. So you go. 632 kappa cancels out with kappa. Yeah. Let's see here. I'm going to write down. I'm going to put the kappa right in here with the number. Okay. And then what we get? We get U naught here. I'm going to put right in here. Here you go. Here you go. Electric potential decreases. Decreases as well. Anything else that we can do? We play with. Let's see. Notes. Final. You go. Stored energy. Yeah. That's do not confuse. Do not mistake. Mix up this kappa the electric constant with K, value of the electric force, okay? So it's 633 right now. And yeah, I think we can